suffering a little bit of light pollution from the town called Benson, which is about a 30-minute drive across the ranch land from where we were observing. Temperatures down there were around 13 degrees. We had about 30% relative humidity. It would go up and down. I'll show you a movie. Maybe I should show you the movie now. No, let's go through the slideshow first, since I'm into it. Again, the Milky Way. You can see the Pleiades right up there. I should get my little red pointer. Oh. The Pleiades are right there, and the projector's not washing it out too much. Maybe this projector's better. There's actually the zodiacal light down to the horizon. This photo on the left is actually a fisheye view, so it's kind of wonky. We had some dedicated observers with us. Laurie Roche. That is Laurie here, actually.
Oh, he's in the bottom.
Yeah, that's Laurie there, doing some observing. It's pretty luxurious because these are go-to scopes. There's 2 of them that we can image. And geeky guys like us can do imaging, and the observers can observe. They have a 25-inch on a go-to mount. Beautiful setup for observing. No challenge finding things. And we can do imaging at the same time, so it's great. That's Diane up there, and she, as you can see, they're on top of a pretty tall ladder because these are Newtonians. But she was observing as well and doing lots of diagrams. 38 Messiers, did you say?
38's new one sketched down there over 2 nights,
Sketches.
2 all-nighters.
Yeah, so that's pretty impressive.
Yeah, I was happy with the opportunity.
Absolutely. And I was after this object, which is called the Angel Nebula. And this is NGC 2170. It's a model stars. Near Orion, actually. So the field of view you're looking at is about 10 minutes by 20 minutes, so it's a fairly small cluster of 3. It reminds me very much of Orion because it has reflection and emission nebula in the same cluster of nebula. It's a lot of fun to acquire images for that. So these are LRGB images using filter wheels and 4 minutes each. Calibrated, and CCD camera, all that good stuff. Now the next one I was prepared to talk about, but John is here tonight. He was not going to be here, so I'll let John talk about this image.
Yes. Okay. I've been addicted to trying to hunt down as many of the galaxies that Halton Park put in his Atlas of Peculiar Galaxies. And the brightest one there, he described as unique because it had this very thin sort of outer spiral arm that you can see quite nicely in the picture. The picture is also interesting to me because there are so many little galaxies in it. I don't know if you can count them all, but there are probably about 15 or 20 galaxies in that picture. And so it's kind of cool.
And use the same equipment as I did, which is the astrograph. It's 3 here. It's an F4 Newtonian astrograph. Has a Paramount. It's on a Paramount ME, similar to what our Victoria Center Observatory uses. And we didn't do astronomy all the time. So we went to Council Rock, which is nearby to where Gary's home is. It's in the Dragoon Mountains, and it was an Apache stronghold. saw a bobcat and other wild animals, lots of birds, birds of prey, especially at the Sonoran Desert Museum, if anyone has visited that, which is just not too far away from Tucson. And finally, we had a rather challenging first night, second day, I guess, as well. We had wildfires about 1 kilometer away from where we were staying. So that was kind of exciting in a bad way.
Yeah.
But thank goodness the wind was blowing in the correct direction and blew it away from us, so that was great. And that is the end. That was the first night. So we had a little bit of cloud challenges. I think we had 2 good nights out of 7 or 8, and we had about a half night, first night. This is actually the first night. That's my report for observing.
Okay, we'll move on to the announcements then. Okay, so from me, we have currently 264 members with 13 in the grace period, so their memberships have expired in the past 2 months. So we seem to be holding our own at the moment. I mentioned in my message this month that we have the plan made for the summer star parties. So we are going to have 20 evenings starting on Astronomy Day, which is April 21st, and that will go through until September the 1st. So those are, so if you're interested in helping out with that, with Astronomy Day, with the summer star parties, or any of our other outreach events, you can let, probably the best person that knows is Ken, who will be saying some a few words later anyways. The other event, and I don't know if Lori, if there's any more details, the Friends of the DAO are holding a volunteer training session on Saturday from 1 till 3:30. And part of that will be the safety briefing for being on the hill. So if people are available this Saturday, that would be a good time to get that in. We ask that all people know the rules for being on the hill because there are some evacuation issues should an emergency arise while we're up there with visitors. That's one of the main messages. Basically, we have to stay put because there isn't room for emergency services to get up the hill if people are trying to leave. I'm short of it. Anything else, or?
Yeah, there are other training sessions that will not take 2.5 hours to see.
No. Yes. Thank you.
There will be, we're training people for some of the other jobs around, and we are in need of other people to come. And you absolutely do not need to be coming all the time. Even if you came 2 or 3 nights on the Saturday nights to help out, we'd be thrilled to have everybody, to have people come and with a lessen the load for some of us. So we'd love to have you up there. We've got jobs in the planetarium and the galleries and the gift shop, the dome. And so if you're interested in any different kinds of things in giving kind of nice like small tours, or if you're interested in kind of some of the merchandising or just talking to people, we obviously need people to be out on the decks and on the parking lot with their telescopes. That's the main part of the night as far as people are concerned. That's what they remember most, is taking the waves, talking to people on the hill. So that's the most important thing. But if you don't have a telescope, that's not a problem. We always need to have people just simply chatting to our visitors. So please, coming up.
Give that some thought, and yeah, if you're available, we'd love to have you participate. Rich, yes.
Hello, everyone. The Sky News for March has got an article about the infant supernova captured by Victor Bussos. an astronomer from Argentina, as well as a lovely story written by Diane Bell, talking about her adventures in the beautiful Gary
Beautiful Wrangler
Sedan.
Mountains in Tucson.
Yes, and so I appreciate you writing that article. Thanks very much. And if anyone else has got something they would like to put forward or submit for the Sky News, I'm not a harsh editor, and I greatly receive your contributions. So keep that in mind. Thank you. And there are a limited number of hard copies of this. If anyone would like to get a copy at the end, please see me then.
Okay, thank you, Rick. One of the things we've been struggling with over the quite a few years is rather windy conditions at our summer star party in Chosen. So we haven't, we've decided we're going to try and find somewhere else. And I don't know if Deb, if you have a brief update, is there any news?
No, that the ponds is sold.
Yeah.
Today, so whoever bought it is taking over. I'm still thinking we should go up there. If you look at it, from Google Earth, it's fine.
Yeah. So if anybody has any leads on potential locations, please let Deb or Bruce know. We've tried a few places, but so far, no takers. So at the moment, we don't have a place. Just to mention that the Cowichan Valley Starfinders do have a star party planned for August, and I should have looked up the dates. So if you are wanting to take in a star party, that would be a good one to go to, just because we can't guarantee at this point we will have one, unless we can find a place.
It'll be September 8th, 9th.
Yeah. Joe, anything from either of your portfolios?
No report from that.
Great, thanks, Bruce. Bruce.
Right now, our member account stands at $7,757. So we've clawed back a lot of our expenditures towards the VCO telescope project. And we're headed back to our regular fiscal responsibility for the next big project down the road. So everything's going pretty well. As I was saying about the star party, we're continuing to look for spots. We've got a line on a few fields out in our centers. If you yourself or anyone you know have an extremely large backyard, plenty of parking, let us know.
No lights.
Yeah, not a lot.
No
Yeah.
lights. That's good.
And thank you, Bruce. Thanks, Roy, for looking that up. So the Cowichan Valley, or the Autumn Star Party, is August 10th to 13th. So. Great. Outreach Coordinator, Ken. Some busy events coming up, but still a bit of time.
Hello, I'm Ken, the Outreach Coordinator. Astronomy Day is coming up. It's our first big event. If you were at Astronomy Day works, or if you want to work at Astronomy Day, it's 10 to 4 at the Royal BC Museum, as I said, on April 21st. People work the morning and the afternoon, all day. The observatory will be open that night as well, so you can work at the observatory if you have a telescope. That's about all I have. Thank you.
Great, thanks, Ken. And there will be other events during the summer, so if you are interested, make sure Ken has your name if he doesn't already. Sid, schools program, about to take a little break for spring break, but you've been full at it.
Spring break is coming. We have been quite busy for the last week and this week. So far, we have 7 presentations. Last Friday, 3 on Monday, 3 today, 1 tomorrow. Anyway, we are waiting for a spring break, 2 weeks off. Also, we have a couple of night sky viewing possibility. So if you are interested in helping, please let me know, or I will be in touch with you. So, yeah, it has been paid for only doing the work of our school program.
Thank you, Sid. We've got the CASCA conference this year, and Jim will say a few words about that.
And especially for the newcomers and visitors this evening, on the 22nd to the 26th of May, the Canadian Astronomical Society, the Professional Association of Canadian Astronomers, will be meeting at the Victoria Conference Center. And we've made special arrangements so that members of the Victoria Center of the RASC or the Friends of the DAO can register at a ridiculously low cost and participate in any aspect of the program that you would be interested in. And there will be a number of talks highlighting the history of the development of Canadian astronomy since the DAO opened in May of 1918. So it'll be a really wonderful opportunity. There will be one public lecture that will be free. That will be on Wednesday, the 23rd, I think it is. And that features Victoria's own Bob McDonald. So there's a lot coming up. But as long as I'm up front, I want to remind everybody that Lori and I would love to see more submissions to Imagining the Universe, the year-long imaging and sketching and craft astronomy-based activities celebrating the RASC's sesquicentennial.
ImaginingtheSkies.ca.
Great, so thank you, Jim. Yeah, thanks for the reminder about that. So that will be available all year, right?
Yes.
Yeah. And there's some great prizes.
Absolutely.
Very good. National Representative Nelson.
As you know, the National Council holds a meeting to which the National Representatives from each center are invited. That happens, I think, 3 times a year. The second one was held on February 25th, and it was supposed to be an hour long, 2 hour long. It was actually 2 hours long, and all of that time was spent by national representatives from the various centers telling people on the National Council about each and every expenditure that they can see, because the focus of all of these meetings thus far, since I've been on council, have been dues increases as a result of rapidly increasing expenses and underpaid employees and things like that. So at the close of our meeting on the 25th, it was decided there would be another meeting or a continuation of that meeting, and the people that had proposed that apparently forgot about it and were just reminded. I see on the email service just reminded them that follow-up meeting has not been scheduled yet, but there's more to come about $3 dues increases, et cetera, et cetera.
And actually, Nelson, while you're standing, the other thing that Nelson is heading up is our revision to our bylaws as required by act revisions within the province. Maybe you could just say a few words about that.
We have prepared a draft of bylaws that are to be revised by the end of November 2018. And the draft has been circulated to members of the Victoria Center Council for their input, and I've done a couple of suggestions. Anything that anybody that's reviewed it has any comments about it, please let me know.
We hope to have that coming forward before the summer break, if at all possible. So that's our timeline at the moment. So more to be distributed to the membership as a whole. Chris.
Oh yes.
Oh, sorry, Chris was just, okay, Nelson.
The AGM.
Yes.
It's open for registration, the AGM council.
Right, okay, yes, the GA, the Annual General Assembly. Is that what you were?
No.
Chris.
Actually, I was thinking of mentioning the GA, but you probably heard in the news the last 24 hours about Stephen Hawking, and I'm mentioning this in the national report because Stephen Hawking is an honorary member of the Royal Astronomical Society of Canada, and we have
a limited number, I think it's something like 8 or 10 spots that we name honorary members for, and he was one of them. So, you know, and this is one of these situations where he brings the honor to us rather than the other way around, I think. So I just thought I would mention that fact, and, you know, unfortunately, we now have to search for another honorary member, which will be looking amongst there are many deserving people, and we'll be looking for that. So I just thought I would mention that.
Okay, oh yeah, Miles?
Today is Pi Day.
Right.
14. Stephen Hawking died on Pi Day. Einstein was born on Pi Day a few years ago.
Yeah, thanks.
Yeah.
Thank you very much.
Galileo died on this day.
International Pi Day.
Matt?
Auspicious day.
An auspicious day.
Technical committee, right, so we have, as I said at last meeting, received some new equipment. We've not yet gone about installing it. Tech committee is holding a meeting on various agenda items at the end of the month, and we will proceed from there. Saturday nights, as always, are open. Check your email. If you don't have emails coming to you, talk to Chris.
Great. Thank you, Matt. Okay, so we have some upcoming events. So we have our observatory open on Saturday nights at this time of the year, weather permitting, of course, and for the active observers. Reminder that Astro Cafe is on Monday evenings, and that will be continuing through May. We have the Vancouver Island Science Fair coming up on April 8th and 9th, and they're always looking for judges. Dorothy has done that for many years. And Lori and David Lee, I believe.
I just, if there's anybody else that's interested in becoming a judge, it's really quite fun. On a Sunday, you're talking to a whole bunch of really very interesting students, and it really is quite eye-opening to see that. So if you're interested in becoming a judge, just let Dorothy or I know. I'm going to be going. Is there anybody else that has already signed up to be a judge?
As a
Great,
mercenary.
thank you. What?
As
Sorry?
a mercenary, I signed up as a judge
Oh, okay, good.
for my business side.
You're business, okay.
And Dorothy.
You know, I'll add,
Yes.
Being a judge is not very onerous. That takes some time, but it's a lot of fun. Well, what we really need, because I'm going to be away, and great, I'm going to be in the 100th birthday party, but for another weekend, because I'd like to be here. But on Monday or on Sunday, the specialties judges who can be completely separate look over for the different organizations that sponsor the fair, which we do, and are needed. And last year it was just David and I, because Lori wasn't here, and to choose or to look, to find if there are any projects which are worthy of our support. And in the last years, there have been more and more. It's a lot of fun. We're looking for projects in basically anything to do related to astronomy, electromagnetic radiation. We had a wonderful radiation project last year, and circadian rhythms of planet, but a planetary science. And it's a lot of fun. You don't have to prepare ahead of time. You just go around and look at the exhibits and pick out a few and decide on maybe up to 3 awards, which then are given out the next day. And I might just add that as in the Senate last year, we had a 5th grader who got an award. Sorry? A 5th grader who got an award, which was a book, the new book, Observe the Universe. Within 24 hours, he sent us a thank you for the book. It was really cool. He hadn't quite finished reading it, and unfortunately hadn't had a chance to use it yet. It was probably been cloudy, and he'd obviously been in school all day on Tuesday. So he may be back with an astronomy project this year, and there'll be others. So think about, or ask Lori or me about it. You don't have to, actually don't really even have to register.
Great, thank you. So if anybody's interested, please and I also have that information, so you can email me to president@victoria.rasc.ca. UVic Observatory, we haven't done very well this year, but we'll try again on April the 13th, which is Friday the 13th. That's very auspicious. And a reminder, the Astronomy Day is on April the 21st. And then I'll mention again that our meeting in April will be in Elliott 167. And how do you get there from here? Well, if you come in through the front door, we're down in this building. Do you have your pointer there, Rich? Forgot to bring one. We come in, we're actually in there. So if you come in here, and instead of coming in here, keep going and go out the door by those chairs and go along the pathway. And through that building, you have to go through the lobby and across a little breezeway into the lecture theater area. And we'll be on the upper floor. There's a hallway in. We'll be on the left side of the hall. Elliott 167. So, and I'll put up signs here, but I really would like to make sure that nobody comes and opens that door that night, because there will be students in here writing an exam. And we don't want to disturb them. So please, and we'll send that out again before the event. Are there any other announcements or anything else to mention? And I'll just remind people that we have the Sky News magazines here. Reg has a few copies of the Center Sky News. Change over here.
It's my pleasure to introduce the speaker tonight, Dr. Vincent Hainaut-Brunet. Vincent was born in Montreal. He got his Bachelor's of Science degree from McGill, and he got his Master's degree in astronomy, astrophysics from Université de Montréal. He then went to beautiful Edinburgh, where he got his PhD, and he graduated in 2013. He then went down to University of Surrey as in a research fellowship near Guildford, just outside of London for a while, and then went to Radboud University in the Netherlands for a short stint. And just this fall, he's arrived in Victoria as a postdoc, Plaskett Fellow at NRC Hertzberg. And his initial talk, he had this lovely title. It was called Globular Clusters, Stellar Laboratories. So he's refined it a little bit, and so it's called Hunt for Black Holes and Globular Clusters. So please, are we all ready to go there?
I hope so.
Yeah.
They're thinking about it. Did we lose one projector?
Right.
That is
It's gone, their site. It's gone.
no, I think we've lost one side. Okay.
No big deal.
Interesting.
Always.
Yeah. We'll just manage without it.
Thank you very much.
Right, can everybody hear me well? Microphone on? Good. Right, thanks very much for the nice introduction. It's a pleasure to be here tonight. I was going to say, after a long journey, but I think you went into much more detail than I was intending. Good. That shows you also how international astronomy actually is. It's also a pleasure to talk about black holes tonight. I used to give talks in schools back in Montreal, and I would talk about subjects completely unrelated to black holes, and at the end, always got a few questions about black holes. So tonight, you're perfectly allowed to, well, people were still allowed, but it's even more relevant if you ask questions about black holes. And I should say it's also quite humbling to talk about black holes the day after Stephen Hawking passed away. I think reading A Brief History of Time, for me as a teenager, was one of the one of the readings that confirmed my interest for physics and astronomy in general. But I haven't studied globular clusters and black holes for my whole academic journey. As a master's PhD student, I was studying massive stars, in particular in young massive star clusters like this region here, R136, in the Tarantula Nebula, in the Large Magellanic Cloud. And then I developed techniques and models that I could then apply to dense globular clusters like those we find, like this one in the Milky Way 47 Duck. And so for the last few years, I've been working on globular clusters. I like to show this image, first of all, because I've used a lot in the past very large telescope instruments up on Cerro Paraná in Chile. And also because two of my favorite objects can be almost seen with the naked eye in this picture. Of course, this is a longer exposure, but the two objects on the sky are roughly the same apparent brightness. R136 is 10 times further, but it's also much younger, so it's 100 times brighter. And when you look at them on the sky, because of this age distance effect, they appear roughly at the same luminosity. But now I focus on these objects, very dense clusters, about 1 million stars. And just to give you a sense of perspective, bringing this back on a human scale, before I delve into the details of what the kind of science we can do with this and how we can look for black holes, I just want to bring this on a human scale, give you a feeling of what it would be to live inside a globular cluster. So can people here raise hands if you would like to be an astronomer living at the center of a globular cluster? Interesting. There's no right or wrong answer. It depends if you want to do a Messier marathon and observe 38 Messier objects in the same night. I don't think you would do that in the center of a globular cluster. So the typical densities at the center of these systems is about 10 to the 6 solar masses per parsec cubed. So that's about 1 million times larger than the typical density around the sun in the galaxy. And so if you wanted to see what the sky would look like inside a globular cluster, if you want to reach the same kind of densities, you bring each star closer by a factor of 100. Then each star, because of this inverse square law for the luminosity of flux, each star is then brighter by a factor of 10,000. And so 10 magnitude difference. A star like Sirius now has the same apparent magnitude as the full moon, but it's a point-like object. So I don't advise to look, well, we'll never find ourselves in that situation, but you wouldn't be advised to look at one of these because they would probably be too bright, and all these bright stars together would probably make the night sky very bright. You'd easily be able to read a book without even the full moon around in the night sky. So it gives you an idea of what kind of systems, extremely dense systems, we're looking at. So the Milky Way has about 160 of these globular clusters, typically from about 10,000 to 1 million solar masses if you count all the stars. They're a very old system that formed at the very beginning of the evolution, formation of the galaxy. Most of them are 10 billion years old or more. And all these stars are roughly same age and same chemical composition, although we're starting to find some interesting deviations from that in recent research. Part of my work is concerned with that, although I won't talk very much about this for the rest of the presentation. And they're also host to a plethora of very exotic objects because of these very crowded environments. You get lots of interactions, compact binaries forming, so lots of X-ray binaries forming in the systems. And they're also very pretty, of course, but that's not the main reason as astrophysicists why we study them. I like this quote from Dutch-born, famous Canadian, Victoria-based astronomer Sidney Vandenberg, former director of the DAO, who said in the conference proceedings, 1980, one of the dangers associated with living on a beautiful island such as Vancouver Island is that it's easy to become insular. For the same reasons, for us, working on globular clusters, finding them pretty and enjoying working with globular clusters, we should also think about the impact that this research on star clusters has on other fields of astronomy. So when I talked about these astrophysical laboratories, I think that's still today, and for the past decades, one of the reasons why we've been so fond of globular clusters, because we can do explore a lot of different astrophysics with these systems. And you see, as an editor of these proceedings, another famous Canadian Victoria-based astronomer. I want to quickly show you a couple of examples of what I mean by these astrophysical laboratories, and then move on to globular to black holes. And so, one main objectives or use of globular clusters in the past decades has been to constrain stellar evolution. So you see a nice example of this here. It's a very deep field HST observations in the center of the globular cluster Omega Cen, which you can actually see with the naked eye in the southern hemisphere. And we'll see a zoom on this region. So thousands and thousands of stars. Omega Cen has about 1 million stars in total, but we're focusing on the field in the very center. And then if you start to rank stars according to their color, which is a proxy for their temperature, this is what we see being done in this animation here. And then you rank them according to their brightness. So the bright, more luminous stars at the top, and the fainter stars here at the bottom. You see what this famous tool that astronomers like to use, the color magnitude diagram, or Hertzsprung-Russell diagram. And so all these stars, as I said, have roughly the same age, roughly the same composition. So what you see here is the effect of mass after 10, 12 billion years of stellar evolution. So massive stars live fast, die young. So you see them here brighter at the top. The fainter stars here still on what we call the main sequence. And then you'll see the... I just want to go back to this part of the animation where we see the color magnitude diagram. Yeah, and then those massive stars, some of these more massive stars will have evolved to become expanded to become red giants, eventually start burning helium and appear as on the bluer side as horizontal branch stars, eventually die, expel their outside layers, and cool down as white dwarfs. So just by studying the infinite details that you see in these diagnostics, astronomers for the last decades have been able to put very strong constraints on stellar evolution. You can also care about globular clusters if you care about how galaxies as a whole evolve. So here I have a map, a density map of stars observed by the Gaia satellite. So every point, actually, we don't really resolve them on this image, but every point is one star observed by Gaia. And if I put labels on these small concentrations that you see here and there, see all these, most of these objects here around the bulge of the galaxy and in the outer halo are globular clusters. By studying the chemistry, the motions of these globular clusters in the Milky Way, but also in external galaxies, we can also make a picture of how these galaxies assemble and evolve. So there's a whole range of applications of using globular clusters for different fields of astrophysics. But in the last, let's say, 5–10 years, but especially so in the last 2 years, they've become quite fashionable to hopefully say something about new findings on black holes in the universe. So I want to, for the rest of the talk, focus on 2 recent discoveries and how we may shed some light on these by using dynamics in the center of the globular cluster. So the first discovery I want to briefly talk about is this detection of gravitational waves in the LIGO detector. So binary black holes, so 2 black holes that merge to produce this gravitational wave event. We know from analyzing the signal that these were 2 black holes with, the first detection at least was 2 black holes with 36 and 29 times the mass of the sun. And so one question that is still being debated by astronomers is how do you actually even form a system like this? It's nothing like what we've seen before. And many part of the answer comes from globular clusters. And the second puzzling observation that we may tackle by using globular clusters is that we're starting to see more and more distant quasars. So I think a couple of months ago you had a talk by Pat Hall on quasars and AGNs, so these supermassive black holes that accrete material, shine very high luminosities, can be observed all the way to the edge of the observable universe. So we're finding more and more of these at very high redshift, very early on in the history of the universe, and it's very unclear how such massive black holes, sometimes with 1 billion solar masses, how such massive black holes could already be present about 1 billion years after the Big Bang. And so the growth of these black holes is a mystery, and perhaps there is a way to seed, to form the seeds for these supermassive black holes in the dense environments in the core of globular clusters. So I want to tackle both of these in turn. So you may have seen these even in the news or in press releases. So this is the first signal detection of gravitational waves from the LIGO detector. So we have two very compact, massive objects, in this case the black holes that are in orbit, close orbit around each other. They distort space-time around them. These ripples propagate all the way to the Earth. And if I rewind this a bit, so using these interferometers, so basically a laser which is going through two paths. Normally the length of the path is the same on both sides. So you have completely so you have the destructive interference. There's no signal, and as the gravitational wave signal as the gravitational wave passes, the length of these arms that are perpendicular, it will oscillate, and you'll see constructive and destructive interference, and the frequency, the amplitude, the exact shape of the form of this signal tells you what objects were orbiting each other, what the masses of these objects were, and so on. So in this case, the detection was of two relatively massive black holes of about 30 solar masses each. And so in the news, days after the discovery, part of the hype was that well, it was the first detection of gravitational wave. First of all, it's quite a feat, success story for human engineering, but also a lot of the emphasis was on the fact that this was confirming Einstein's theory of relativity. Well, actually, if you'd asked astronomers even a few years ago, or a couple of decades ago, we already had good reasons to believe that these gravitational waves did exist. We didn't have a direct detection of these events, but by looking at, in particular at this system, binary pulsar, discovered by Taylor and Hulse, which eventually got them the Nobel Prize, you can see that the period of the system, which is timed very precisely by these very regular pulses coming from the pulsar, so one of the objects in the system. The period of the system as a whole is slowly declining with time, and the prediction is and the observations are in perfect agreement with the predictions that you would expect you would get from emission of gravitational waves according to Einstein's theory of relativity, which is by measuring the period of this pulsar over time, there was already some pretty convincing, although indirect, evidence that gravitational waves did exist. So the detection in itself was actually worth the Nobel Prize for gravitational waves, but it was not really confirming. Well, it was confirming, it was not the first confirmation of the theory of relativity. I think one more surprising fact about this detection and discovery is the masses of the black holes involved. So if you look at in purple here, at the masses of the black holes that we knew nearby in the galaxies that have been studied with X-rays, sometimes detecting their companion, looking at binary motions to measure the masses of these systems. All of these were between a few solar masses to 15, 20 solar masses. And suddenly, in the time span of a year and a half, we discovered 4 black hole binaries that gave rise to gravitational wave signal, and they're more massive than anything we had seen before. And it is quite challenging to actually get these black holes in a binary system that is so close that eventually it will merge and produce gravitational waves. So quite a loaded slide. Don't worry about the details here on the right. It's just to hypnotize you and show you how complex it is to actually end up with a system with 2 black holes in orbit around each other in a very, very close orbit. And the reasons for this is that first of all, massive stars, as they evolve, we saw that on the nice color magnitude diagram earlier. As they evolve, they expand, they become brighter. So massive stars, if they have a close binary companion, they would eventually engulf their companion, completely eat it, so you don't have a binary system. After that, you just have one star that eventually may make a black hole, but not a binary black hole. So that's one problem. And also when massive stars end their lives, especially the more massive stars, they create a black hole, but this supernova explosion that creates the black hole is often, also we think, accompanied by a kick. So the object that, so the black hole that is formed by the supernova explosion gets a kick through space. And we think that these kicks may be large enough that in most cases they would disrupt the binaries in which these systems may be been placed originally. So if you start with 2 massive stars in the binary system, it's more likely that either you eat your companion or you lose it after one of the components has exploded as a supernova. And all the steps that you need to follow to finally get to a system that has 2 black holes are extremely uncertain. It's very detailed binary stellar evolution. It's very hard to predict. We can predict it, but there's a whole range depending on the assumptions that you use. If you take the values that were proposed in the literature before the first detection of gravitational waves for how many of these black hole binaries we should find in our local patch of the universe per year, the predictions range all the way from 0.1 of these systems per year to about 300. Not all of them are of large enough amplitude or close enough that we can detect them, but that's the typical units that we use. But a large range of predictions. And if you just take the detected event at face value and you infer a rate from that, the estimates are more like between 10 and 250. So consistent with the upper limits of what had been suggested just from theory before. But eliminating a lot of reasonable scenarios where you just use stellar evolution binaries and end up with 2 black holes in the binaries.
Vincent,
yeah.
What is the volume? How big is that volume?
So the unit here is gigaparsec cube. So gigaparsec, so like it's an enormous number of galaxies, like encompassing local group galaxies. And just make a sphere out of this or a box out of this. That's the volume we're thinking about. That's just a way to express how many of these we should find per unit volume of the universe.
So these are sparsely located.
Yes, they're pretty rare, but as a matter of fact, we've only detected 4 of them in 2 years of, well, the detector is not running all this time, but in 2 years of LIGO activity, only a few events have been detected. Yeah, so they'll come back. Yeah, all that to say that, the estimates that we get just from observing these events are quite high, and the predictions from stellar evolution, some of them, if you tweak some of the assumptions, you may be able to reconcile with what we observed, but it seems like we may need another way than just starting with two massive stars and a binary to end up with a closed black hole binary that gives gravitational wave signature. So here come W clusters. So one way, the other possible promising way that has been imagined to produce these events is to create these binaries just dynamically by stars interacting in the dense cores of clusters. So you don't quite see here on the left, that's an artist's impression, visualization of a simulation with lots of stars interacting inside a globular cluster. You don't see the black holes, but you see the light in the background that's bent by the gravity of these black holes in the foreground. You see all these interactions with visible stars. On the right is just zooming in or isolating one of these possible interactions between two binaries so that meet each other, interact, oscillate a bit, eventually will exchange companion, kick out one of the stars, and the energy that is released by kicking out one of these stars can actually make one of the binaries even tighter. So very intense, active environment. All this just to show you that in these environments, you can create black hole binaries from configurations or binaries that didn't have two black holes in the first place. And that's useful because now all these problems with engulfing your companion stars or kick velocities, disrupting binaries, then you can sort of circumvent that in the center of the globular clusters. So do we actually expect to see black holes in clusters today? So if you just take 1 million stars and the mass distribution, so the number of low mass stars and more massive stars that we typically see around this today, how many stars are massive enough that you end up with a black hole after a supernova explosion? So this is also very uncertain. It depends on what you assume for the mass distribution of these different stars, on what you assume for these natal kicks that I was talking about. That's also very uncertain, but you may lose black hole altogether when they form because they receive these kicks and escape from the cluster, so you wouldn't observe them today in the globular cluster, but the numbers typically are a few hundred to a few thousand black holes that we'd expect to form initially in the globular cluster. And then what happens is that quickly, because these black holes are typically much more massive than the average star in a cluster, 10 times more massive, roughly, they will eventually sink, actually quite quickly sink, segregate to the center of the cluster. And up until a few years ago, we thought when they sink, black hole systems start interacting with each other, and then they can very efficiently interact, give each other kicks, and expel all the black holes from the cluster. Now we know from more realistic models that this will happen, black holes will start to interact, but not to the point where you completely deplete the population of black hole in a cluster today. So the more recent numerical, theoretical models looking at the evolution of black hole systems in clusters predict that we retain a fraction of them. And so, okay, we have good reasons to now go and look for these. So one thing you can do is look for X-ray emission from these objects. So you look here at the central region, zoomed in on the central region of this famous cluster 47 Tuck, and you see in X-ray all of these X-ray sources. But actually, not only black holes can emit X-rays, neutron stars too. So these X-rays are typically produced by material being accelerated and heated, eventually accreted onto the compact object, whether that's a neutron star or a black hole. So both neutron stars and black holes can emit X-rays, but black holes will typically also have radio jets that can be observed. So the way that people have gone about trying to differentiate neutron stars from black holes in these X-ray maps is to look both at the radio luminosity and the X-ray luminosities and compare with what we know from neutron stars and black holes nearby, which they're much more nearby than in globular clusters. So sometimes we see the companion, we see the orbital motion of the binary. So these systems in black are confirmed nearby black holes, and these systems these points in blue are confirmed neutron stars in the Milky Way. And now you do the same for more distant X-ray radio sources in globular clusters and see if they lie more on the line that agrees with neutron stars or on the line that extrapolates from the black hole observation. And there's a few more, so these yellow points are some of the recent detections. There's a few more globular clusters now for which one or a few of these objects which have radio and X-ray luminosities consistent with black holes have been found. And there's even a few more than what are shown on these plots. So if you look at an actual image, that's what it would typically look like. X-ray images is plenty of sources, so neutron stars, pulsars, black holes. But if a point shows on both the radio and the X-ray image, it's typically a good black hole candidate. You don't know for sure. You have to follow it up, try to determine what kind of companion it has, or what kind of binary it sits in. Just by observing these X-ray radio emissions, you can have a good idea if it's a reliable or promising black hole candidate. As I said, the number of these systems is increasing. About 25% of the clusters for which we have good enough X-ray and radio data, there is at least one candidate black hole that has been found. And there's a few more serendipitous discoveries of black holes, not from X-ray or radio, but just by monitoring the spectra at different points in time, multiple epochs, for lots of stars in the central regions of globular cluster. So here's a case here, HST image in the field in the center of a globular cluster. That's there, an image from the MUSE in a spectrograph. So every pixel on this image, for every pixel, we also have a spectrum. So we can determine the shifts in the absorption lines of the stars from the spectra, see if they're moving. And this object pointed here, as a function of time, we see that the velocity of the star with respect to the Earth, to the observer, is varying by a large amount, by more than 150 kilometers per second. From that, you can infer, or at least put a lower limit on the mass of the unseen companion of the star that we see in the image here. And so just by looking at the wobble in velocity, what is shown here, serendipitously people discovered black hole. But we only know in total of a few black holes in a small number of globular clusters. How then can we have any hope to estimate rays for gravitational wave events and know what's the total amount of black holes in these clusters? So one thing we should bear in mind is that for every black hole that you see, because it's producing accreting material and producing X-rays and has radio jets, there's probably a completely much larger unseen population of black holes that either have the right type of close companion or don't have a companion at all. So this is another part of the research that's quite uncertain at the moment, but there's more and more models probing this, modeling the full dynamical evolution of globular clusters and trying to compare the number of black holes that you get after 10 billion years, number of black holes that you get that are in a configuration where you would detect them in X-ray and compare that to just the total number of single black holes that don't have a companion, don't have the right companion. And it's typically a factor of 100 or 1,000 difference between the two. So for every black hole that we detect, it's probably a large unseen population of unseen black holes. But unfortunately, we'll never detect these with the traditional techniques. So part of my work in the recent years, in the last year and a half, I would say, has been to try to find new ways to probe the effect of black holes and to, if you want to, weigh populations of black holes in clusters, but looking at indirect effects that they have on the dynamics and the structure of these clusters. So, but before I should say, so what are the ways to make progress and uncover these whole population of black holes? So one promising way is at least to establish if this dynamical formation scenario in clusters actually works, or to identify systems that came from this formation channel. One way would be to look at the spin of these black holes. So up to now, the data or the signal are not strong enough to do that, but if you have a strong enough gravitational wave signal eventually in the future, you can measure the spin of the two black holes, the spin of the two black holes just from the shape of the signal, details that I won't go into. And if you see that the spin of the two black holes are aligned, then there's a good chance that these two black holes from their birth were part of the same binary system. So, and if these spins align with the orbital plane, especially, and if you find misaligned spins, it's more likely perhaps that these black holes were just dynamically formed by black holes that were not part of the same system initially, and that just encountered each other, formed a new binary system in the center of the cluster. So that's one way, but future will tell us, and that will depend on future LIGO detection. So eventually, yeah, we want to measure these X-ray radio fluxes for more of these systems, find more and more candidates, but as I cautioned earlier, we'll probably just find the tip of the iceberg by doing that. So what I've been doing is try to come up with models that include the effect of black holes and uncover these all these hidden black holes. And so you may wonder, well, how do you do that? You don't see them. You don't see any light coming from these systems. Well, there are gravitational collisions in these clusters. The low mass stars in these systems, they know about the black holes. They've had plenty of time to just come across each other. They don't necessarily go into encounter other stars, have physical collisions, but just by cumulative gravitational effects and encounters from nearby and more distant stars, over time these stars exchange energy, and what you see is that the more massive stars, they will lose energy to the lower mass stars. They get lower velocities, sink to the center of these clusters, and on the other hand, the low mass stars, they gain energy, they gain velocity, and move to the outskirts of these clusters. And that's an effect that's now well quantified by numerically simulating these systems. So that's what you see as a function of time: black holes sinking and low mass stars being pushed out. And this leads to predictable equilibrium. You don't have necessarily all the time to start from initial conditions, place stars around, evolve the system with Newton's equation of motion for 12 billion years in a computer. You don't always have to do that. You can just take into account the fact that these low mass stars and black holes will reach some kind of equilibrium and describe these systems as static systems. So we now have these analytic models that take into account the different distributions and velocities of low mass stars and black holes in these clusters. If you only care about what clusters look like, how many black holes they contain at the present day, and that's perfectly a good shortcut to make. You're only interested in the current distribution of stars. And you can apply these models to data and trust that they reproduce the different distributions of stars and black holes accurately, and eventually, just by looking at the visible stars, infer the distribution of black holes. And so I won't spend too much time with this. It's more technical, but it's just to show you that by using positions and velocities of stars with HST and with spectrographs that we have on 8-meter telescopes on the Earth, we can quantify the spatial distribution and the velocities of the bright visible stars, the one that we see on images, and apply these static models that tells you how the black holes behave with respect to those bright visible stars. And so that's what I've done here, but on mock data. So that's idealized data. We take a full simulation of a cluster, see what it looks like at the present day, and try to reproduce what we would do when we look at the sky with a telescope. And so that's just all the different observables that I'm dealing with, trying to gather and fit in my research. And then from that, particularly in this case, because we have all the information, we know how these stars are distributed, even the black holes in the idealized simulation. You can see how these models do at predicting the masses and the distribution of black holes. There's lots of quantities that you can look at, but maybe let's just focus here. That's what we call a mass function. So number of stars as a function of mass of these stars or remnants, black holes, in funny units. But what you can see is that by applying these static equilibrium models, we're able to at least roughly to reproduce the mass of the black holes, which we don't directly observe, we don't directly fit on, but it comes out in this case of these nice models that we can apply. So there's lots more testing that we're doing, and that we're trying to quantify what are the possible biases in a method like this. But in the future, in the next years, that's certainly a way that we're planning to use to then uncover all these black holes, not just the few ones that are detected in X-rays. And there's cases where it may be even easier. You don't have to worry so much about the details of the method. The fact that you have, just by looking at the distribution of stars of different masses, so here the different lines correspond to stars with, in this case, low mass main sequence stars, or more massive binaries, what we call blue straggler stars. The important thing here is that all these lines correspond to stars of different masses, and if you look at their distribution with radius in this particular cluster, and you see 61.1, they all lie on top of each other. And so that's quite unexpected. I described this picture earlier where the black holes sink, the massive stars are pushed out a bit, but not as much as the very low mass stars. In this cluster, we have something that is more like this. But that's not completely unexpected, or at least we can find a way to come with a configuration like this. If we put even more black holes in a system like this, the difference between the high mass stars and the low mass stars will eventually decrease. And for a large population of black holes, basically any other stars, whether they're a 0.4 solar mass star or a star with the mass of the sun, they would all be pushed out to the other parts of a cluster. And by having a large population of black holes, you can completely suppress this mechanism of mass segregation. We compared some of our models with different contents of black holes for this particularly extreme cluster, and we find that we need to retain about 50% of the initial population of black holes. So we're talking several hundred black holes to completely suppress this mass segregation between stars of different masses. So we have to check that with further observations, but that's one very promising candidate where what we see in the distribution of stars seems to indicate that we could have a large population of black holes. Now, this signature is also degenerate with another type of black holes that could be lurking at the center of these objects, and that's what I want to spend the final part of the talk on. So you can also have what we call an intermediate mass black hole, so something in the range of 100 to several tens of thousands of solar masses. If such an object is at the center of a globular cluster, it will have a similar effect to a large population of black holes. Stars will interact with the central object, be scattered to large radii, and you may end up with a smooth distribution of stars, regardless of their mass. Stars with the same distribution. So we want to see if some of these clusters host intermediate mass black holes. And it's also relevant to understand these supermassive black holes that I briefly mentioned earlier. So basically, every massive galaxy that we can observe seems to host a supermassive black hole from about 1 million solar masses to several billion solar masses. As I said earlier, some of these are now found at redshifts that imply that they were already in place only about 700 million years after the Big Bang. How do you grow such objects? Well, in these intermediate mass black holes, if you can quickly form them at the center of the globular clusters, and then clusters merge, are accreted by galaxies, merge with the central parts of these galaxies, they may offer a way to quickly make large seeds for these supermassive black holes and help to grow these much faster than if you just had to encounter a black hole and accrete stars in this black hole and merge with only small objects or black holes. And so that will offer a way, if these intermediate mass black holes exist, will offer a way to maybe to form these supermassive black holes. And if you typically look at the mass of the black holes found in these large galaxies and the solar mass related to luminosity and the amount of mass found in the central part of these galaxies, we find a nice correlation. If this correlation extended all the way to the masses of globular clusters, you would expect black holes of about 1,000 or so solar masses in the center of these systems. They haven't been unambiguously detected up to now, but we may expect them to form in this system. And the way you do this, again, it's very uncertain, but simulations suggest that if you start with dense enough systems, there's lots of interactions early on, you can actually have physical collisions, not just gravitational encounters, but physical collisions between objects. And if that happens quickly enough, you can grow to a mass of 2,000, 3,000 solar masses, depending on lots of assumptions and initial conditions. But you could end up with a central object that is quite massive that may leave an intermediate mass black hole in the end. And so now the question is, how do you actually detect these intermediate mass black holes? We've seen that some of these signatures are maybe degenerate or similar to what you would have from a population of stellar mass black holes. But you can also use similar techniques, for example, looking for radio or X-ray emission. But the current constraints, just by staring at the clusters with radio or X-ray telescopes, the current limits are very low. We don't see any obvious signatures of the strong X-ray radio emission that we would expect from intermediate mass black holes, but perhaps they're just not accreting. There's not much gas around in the center of globular clusters. Typically, it's lost by stars and expelled from the cluster. So perhaps they're still there, but just not accreting a lot. So then you have to rely on indirect techniques. So typical way this is done is by looking at the velocities of stars in the small region around the black hole. So what we call the sphere of influence, the region where the gravitational potential in the center of the cluster is dominated by the gravity of the black hole. You can estimate what size this region has for typical masses that we expect for intermediate mass black holes, for typical velocities of stars that we see in the center of globular clusters. And you end up with a spatial scale that is smaller than an arc second, so more than 2,000 times smaller than the full moon. And you need to measure velocities for a large number of stars in that small region, and maybe if you can do that, you observe a rise in the central, what we call the velocity dispersion, so the typical velocity of stars in the system. You may be able to then see a rise in this very small region and infer the presence of the black hole. But this is observationally very challenging. There's been claims based on all sorts of data, typically from data where crowding of stellar sources is very important. And so there's no clear detection of such a large rise in the velocity dispersion in the central arcsecond today. So no claim, at least, is unambiguous. Then you have to look into slightly more indirect effect of black holes. So not only an intermediate mass black hole would give a sharp rise in the very inner regions, but it may also elevate the velocities of stars a bit further out, up to a parsec, so something like 100 arcseconds from the center of the cluster. And so some of the work that I've been doing in the last year or so with collaborators has been to look at other ways where we may get an extended rise in the dispersion. And I don't have time to go into much of the details, but without even putting a black hole in the center of the cluster, if you start to look at other complications, like how are the orbits arranged? Do you have lots of eccentric orbits in the center of the cluster? And you look at these orbits only along the line of sight, so some stars may be actually coming from far out in the periphery of the cluster, plunging at high velocity towards the center, and creating artificially a rise in the central dispersion of velocity. So there's other ways, and we're starting to quantify the degeneracies between these effects, but it looks like if you're looking just at the slow increase of the dispersion in the inner, I don't know, something like 100 arcseconds in the center of the cluster, there's other reasonable ways we can think of doing that, including populations of stellar mass black holes. So an intermediate mass black hole would increase the velocity by a large amount in a very small region in the center of the cluster. But if you have a small system of black holes, stellar mass, so 10 solar mass black holes that sank to the center of the cluster, and you model the effect that these have on the velocities of bright stars that you can observe, then you can also get these rise, similar rise in the central regions as you would get with an intermediate mass black hole. So it's not clear at the moment that any of the kinematic information, so velocity information of stars that we have in the central regions of clusters are actually telling us that there's a black hole. So we'll have to eventually probe these regions at higher resolution with some of the instruments described above. So I put here's some of the facilities that we can use now and in the near future to make progress in this issue of intermediate mass black holes. So Gaia is a European satellite. Lots of people in the Canadian community are planning to use the data, but the funding is from Europe, and Gaia will map 2 billion stars in the Milky Way, measure very precise precision, and so on a 5-year base time scale and baseline, you can see very minute changes in the position of the stars and measure velocities of stars in a cluster on the plane of the sky. And so that will tell us, for example, if stars and clusters in the outskirts have very eccentric orbits, if this create these effects of that mimic signatures of a central black hole. With a combination of the Hubble Space Telescope and James Webb Space Telescope, you can do something similar, but for much fainter stars and focusing on the central regions of globular clusters, so measure positions very precisely, measure velocities very precisely with a long baseline, and eventually, if you go and can observe enough faint stars in this very tiny region, 1 arcsecond in the center of clusters, you may be able eventually to see a steep rise in this inner region, and that would be a smoking gun signature of a black hole. So if we wait a few years, combine the data from these 2 instruments, we may have an answer there. And also I mentioned an instrument that's currently being built by Canadian astronomers in Toronto, but also here at NRC and the new VIC. So what we call an IFU, so these instruments that get you one spectrum for each pixel on your image. So this particular instrument, GearMass, will be placed on Gemini, and also assisted by adaptive optics. So you could have similar resolution to having a telescope in space, but on the ground, and measure velocities for all these stars in the very crowded regions of clusters, and also hopefully eventually see the signatures of these central black holes. So just to summarize, there's growing evidence for the presence of some stellar mass black holes in globular clusters, but as I said, that's probably the tip of the iceberg. We're working on methods to using dynamical models to constrain the total amount, fraction of black holes in these systems. But when we do that, I think we'll have a much better idea of how dynamical formation of black hole binaries in the center of clusters could contribute to the gravitational wave sources that are seen with LIGO. And finally, there's no ambiguous detection of intermediate mass black holes. People are still working on that, arguing, debating if the signatures that have been seen are unique to intermediate mass black holes or could be explained by other effects. But it would be very exciting eventually to find one of those. It could explain some of the early growth of supermassive black holes in the early universe. But future will tell, and future instrumentation will tell if these intermediate mass black holes are lurking in globular clusters. And I'll stop here. Thanks.
Well, thank you very much, Vincent. You started me off right off the bat imagining what it would be like in downtown M13, right in the middle of a globular cluster. And that sounds to me like it'd be a very, very bright place to be. And I'm thankful that we're living in a rural area of the galaxy rather than right in the downtown core. So that's great. It's fun to imagine that. The one horror story I had is that, let's say you were a student and your project was to count how many stars were in a globular cluster. And did you ever worry about that? Or how do they estimate how many stars are actually in a globular cluster like M13?
Well, so first of all, the stars that we see in globular clusters with the typical exposure time tens of seconds, a few hundred seconds, these are still the brighter giants, horizontal branch stars. So they're actually a small fraction of all the stars in the cluster. So you may see in a typical image a cluster a few thousand stars, and that's a percent of the light of the cluster. But if you had to count all of them, even though there's just a few thousand, then I would write a computer program or use an available computer program and do that automatically. I wouldn't do it star by star.
Well, thank God the computers are around. And it struck me is that you're using these tools that just came rolled out in the last couple of months, like LIGO and that is used. It seems to me like you're right in the right place at the right time. It's so candy.
I'm not part of this huge LIGO collaboration per se. It's just that, as I show, these results are interesting and have interesting implications.
Absolutely.
But I'm not part of the.
Well, I understand that, but they do mesh quite nicely. So has anyone got some questions for Vincent?
I want to know where I can get a copy of that wonderful video right at the very beginning, where all the stars went into the HR diagram.
I will send the link to make it available.
Awesome.
Yeah.
That was stunning. Anyone else? Les.
I have a question more related to the sociology of astronomy. You know that I think it's widely perceived that astronomers are considered to be nerds. And I'm just wondering, given the high-profile nature of black hole astronomy, whether there is a type of astronomer that might have the acronym, the initialism, BHPA, that is a black hole Playboy astronomer. Because black hole astronomy might be more sexy, and I wondered from your personal experience whether you have found it useful in interactions with women to talk about.
We can maybe discuss the women part at the coffee later, but just like in terms of public outreach, that's kind of what I was saying at the beginning, that just the words black holes, they tend to just ignite just a special interest in people. So I don't know, I think in the research community, black holes are one topic among many others. It's not necessarily more sexy to talk about black holes at a conference than it is to talk about RGB stars. Sometimes it is because of LIGO or circumstantial reasons, but with the public, certainly I find that if you give a talk in school or at a star party, then black holes tend to be a good candidate.
Okay, well, thank you again, Vincent. As a token of appreciation for your talk, we have a couple of Victoria Center t-shirt for you, and the Royal Astronomical Society of Canada with some sort of telescope that you might have seen. So thanks again very much for your